This figure illustrates the composition dependence of the direct and indirect bandgap energies at the gamma, X, and L points in aluminum gallium arsenide at 300 K. On the horizontal axis, we have the alloy composition ranging from gallium arsenide at X equals 0 to aluminum arsenide at X equals 1. On the vertical axis, we see the bandgap energy, and on the right side, the corresponding emission wavelength. So we see several curves are plotted here. They correspond to the bandgap at different high symmetry points, including the gamma, L, and X points. The lowest of these determines the actual bandgap of the material. At small aluminum compositions, the gamma value has the lowest energy, so the material is direct bandgap. As X increases, the gamma bandgap energy rises rapidly. Meanwhile, the X value energy increases more slowly, as shown. At approximately X equals 0.45, the gamma and X curves intersect. This is the direct to indirect crossover points. Beyond this composition, the X value determines the bandgap. The corresponding emission wavelength at this transition is about 624 nanometer. This is why aluminum gallium arsenide-based lasers typically operate only below this aluminum composition. This slide shows a table of empirical expressions for the bandgap energies of various ternary 3-5 semiconductor alloys at 300 K. These expressions were compiled from experimental measurements. For each alloy system, the bandgap is given as a function of composition X. So we see that except for aluminum indium phosphide and gallium indium arsenide, which follow a linear dependence of the bandgap on the composition X, all other expressions have the form of E sub G naught plus Bx plus Cx squared, which again reflects the bowing behavior we discussed earlier. Also, as previously noted, aluminum gallium arsenide is a direct bandgap material for X smaller than 0.45 and becomes an indirect material for X larger than 0.45, where the conduction band minimum occurs in the X valley and the bandgap energy follows a different relationship with X, as shown in this expression. Another material having a direct-indirect crossover in the bandgap versus composition X is aluminum gallium antimonide, as shown in this table. So these formulas are extremely useful for device engineers because they allow us to predict the bandgap for any composition. This information is essential when designing laser diodes, LEDs, photodetectors, and heterostructures, since the device wavelength is directly determined by the bandgap.